Hello everyone, I'm Peiwei Hu from the University of Chinese Academy of Sciences. I'm happy to share our latest research, AURC, detecting errors in program code and documentation. First, I will introduce the background of our research. Nowadays, modern software is becoming more and more complex with enriched functionality. It's expensive and time-consuming to develop common components from scratch. Instead, modern software will involve a variety of open source libraries to meet various requirements. So the structure of modern software is like the pyramid in the picture in the left. The open source libraries form the base of the pyramid and underpin the practical software at the top. However, if the open source library suffers from the security issues, it will also affect the practical software. For example, the Log4 shell vulnerability exposed the year before can affect more than 1,800 downstream products. Thus, it's very important to detect code bugs in open source libraries. Currently, the code bug detection usually depends on several substances. For example, some studies will extract usage from documents and use the extracted information to detect code bugs in program. However, they assume the documents are correct. They also assume the API that code bugs involve are described in the documents. Some studies will extract plenty of API usage from the code base and decide the correct one based on majority voting. They assume the most used usage is correct. Some studies will detect code bugs based on the behavior in the similar context. They assume the correct usage will exist in the similar context. However, we think these three assumptions are not reliable. Both documents, the majority voting, and the usage in their similar context is not trustworthy. So let's think about how would an experienced programmers find the usage facing the unfamiliar API. She or he may read documents, may scan the source code of API, may figure out how the existing code use the API. In fact, these three methods correspond to three objects in API invocation. We call them API usage reference, or AUR in short. They include document, COI, and the core. Our method will extract information from these three AURs and cross-checking these three AURs instead of just use one or two of them like previous studies. The picture in the left shows the overall workflow of our method. We propose different techniques we will discuss later to extract information from document, COI, and core. After cross-checking the information, the AURC will perform correctness inference to decide which AUR should be modified to recover the consistency. And the picture in the right shows a detailed example about how AURC works. Currently, AURC focuses on incorrect return check. So first, it will extract the return values from the COI. As you can see, the return values contain -1 and another API invocation, which is bn to bandpad. According to our design, while analyzing this COI, the return values of bn to bandpad will already be predicted and available, which are -1 and greater than 0. So after taking the unit, the final return values of the COI are -1 and greater than 0. After analyzing the documents, AURC will also get the return values of this API, which are -1 and greater than 0. They are consistent. Then AURC will extract the information from the core. It will find the case, which is case 3. In case 3, the negative and positive return values are treated as the same execution status. So it's inconsistent with the information from COE and the documents, there is inconsistent. So correctness inference starts working. And according to the first rule, documents and COEs are consistent. So we should fix cores. This is how AURC works. Also, we solve some challenges during the research. For example, during the extraction of COE, two factors will lead to heavy analysis. The first is long call chain. To solve this, AURC will analyze the COE according to the topological sorting of the call graph. This way, if the return value of the API depends on another API invocation, this API is already predicted and its return values are available. So we can do the replacement to convert the inter-procedure problem to an intra-procedure problem. The second is the return statement will locate at the tail of execution path. So the traditional forward analysis will lead to extra analysis cost. For example, in the picture in right, if we want to get the variable RET, right, we just need to backtrace the statement. Just the 1 or 2 statement, we can get its values instead of start analyzing from the start line. Considering this, we propose context-sensitive backtrace prediction. It will perform backward analysis by iterately searching for reaching definition of the variable. It also contains several context constants to improve the accuracy. So there are also 2 factors will hinder our analysis during the analysis of documents. First is the documents may contain sentences that are irrelevant to the return values. The second is documents may describe the return values with natural language instead of the number or range. This will affect our automatic analysis. To solve this, AURC involves a BERT-based classifier to filter out the sentences that are irrelevant with the return values. It also owns a mapping table to map the natural language to corresponding range and numbers. After finding the inconsistencies, AURC will try to give suggestions about which AUR should be modified. After analyzing abundant patches, we propose 4 rules for correctness inference. Take the first rule as an example. If the COE and the document is consistent and they are inconsistent with the core should be modified to recover their consistency. This is because the error is caused by the API users. He or she made a mistake. If the core and the COE are consistent and they are inconsistent with the documents, this means the code can execute normally. So the most safe way is to update the documents. And we test our prop type AURC on 10 code bases. It can find over 500 code bugs and over 200 document defects with false positive 12.1% and false negative 9.1%. We also tested the components of our prototype. For example, the average accuracy and recall of our classifier 95.5% and 94.3% respectively. We also define coverage COE for sort to evaluate the effectiveness of our backward analysis. The result shows that compared with forward analysis, backward analysis can save the analysis of 88% of code. And we also define pass rate to evaluate the effectiveness of topological sorting and the API replacement. The result shows that it can save the analysis of 99.94% passes. So until now, over 200 of code patches and over 100 document patches have been merged by maintainers. And with the help of AURC, we rank top 25 in all 800 contributors of OpenSSL. We also get positive feedback from maintainers. So let's make a summary. First, we propose a new method to detect defects in both code and documentation by cross-checking 3 AURs. Secondly, we propose techniques to extract information from AURs, including documents, COIS, and CORs. We also test our prototype on real-world code bases, and over 200 code patches and over 100 document patches have emerged by maintainers. And that's all. Thanks for your attention.